And then if we look at infiltration, infiltration is very interesting. We sometimes get very little sensitivity to infiltration and temperature, except in the fallow field where it would increase a little bit. But we tend to get an increase in infiltration, decrease as precip declines. And then, of course, expected behavior as volumetric soil moisture declines, we get an increase in infiltration. So soil moisture is an interesting one in all this. We get a collapse in snowmelt runoff, but infiltration into the spring soils increases as things develop into a drought. If there's enough water. It's simply because we have much drier soils and much warmer conditions in the spring, or perhaps multiple melt events, or snow melt occurring earlier and much more slowly. And all these things can increase the infiltration rate into the soils. And so there's an essential stability in soil moisture under drought conditions that is not there for the runoff. The runoff flips on and off like a light switch. And the soil moisture, the whole system is now effectively, as things dry out, effectively to pump any available water into the soil moisture in the spring. So and again, why would we have a cessation of spring runoff? Well, this is taking a snowpack as it existed at that time and then warming it up by 5 degrees, and now we get 3 different snowpacks developing over the winter, and a much shorter winter and a longer spring and greater evaporation losses. And if we decrease precip by 50%, again, we get a collapse of the winter snowpack. It's continuous still, but it's not nearly as much as only maxing out at about 30 millimeters water equivalent. It's not very much. So we can look at some mechanisms using the model in this case. So now we can start to look at the summer period as analog to the winter period, and what happens with evapotranspiration as we look at various conditions. And in this case, remember, we're modeling the whole winter period, the spring period, and then the summer crop growth and evapotranspiration, using evapotranspiration models that are coupled to the soil moisture, using the soil water withdrawal curves, and making certain assumptions about rooting depth and plant growth. So some people suggested this should be easy. If there's no runoff in a drought, then the precip and evapotranspiration should be equal to each other, and that's drought hydrology. It's not quite that easy because of the change in storage, and it's particularly important in the prairies, and what's going on with soil moisture and how many years does it take to deplete that. And it's very dynamic, and we also have change in rooting depths. Plants want to live. And so if there's not water in the shallow zone, they will actually, particularly the grasses, will send the roots deeper and deeper during their drought. And so when you're modeling this, you have to be very careful. You can't hold that parameter constant during a drought, or you'll be wrong. And then during wet periods, plants don't need to send their roots so deep, and they compete for water in the shallower soil zones. So let's look at we'll set up a simple model here. Rooting zone, a deeper soil zone, groundwater we won't worry about too much. We're going to look at evapotranspiration coming out of largely the soils of the crops in this case. And so here's a simulation looking at the early 70s at Bad Lake. Here's the soil moisture. It's hovering around 200 millimeters of storage, going up and down over the year. This is from the end of May up until the end of August. Here's the rainfall in green accumulating very quickly, about 220 millimeters, lots of it over that summer. And here's evapotranspiration, largely coupled to the rainfall until we get into August, where rainfall now starts to exceed evapotranspiration. The plants can no longer take advantage of the rainfall because available energy is dropping off and plants becoming senescent. And so we have just little bits of runoff occurring, mostly in late summer in this environment. So now and that's a non-drought year, a classic non-drought year. So now let's put it into a drought. So we'll put the system into shock. We'll start with year 1. We've taken the rainfall and divided it by 3. We've warmed up the temperature by 3 degrees. And what happens? Well, soil moisture started off the same, but it starts to drop off. You see it's starting to deplete over the summer. Rainfall is much lower. Evapotranspiration is greater than rainfall because it's depleting soil moisture, and runoff has collapsed. So runoff, very similar system in the summer to what we had in the spring. Runoff is like flipping a switch. We're into extreme hydrological drought, and yet if you look at the evapotranspiration, which might be an indicator of plant growth, has not suffered to the same degree. Let's carry on. So now we've really gone after it. We've reduced precip to 1/3. We've increased air temperatures by 3 degrees. And we've taken that initial soil moisture in the spring and divided it by 4 arbitrarily. So we're saying that it was a bone-dry winter, and we've been into several years of drought. Now we have a severely limited evapotranspiration that's essentially following along the rainfall pattern. Soil moisture just can't recharge very much at all, and runoff is 0. So the very depleted system here with very, very low evapotranspiration. We're going to get very high surface temperatures as a result of the low transpiration occurring in this system. So in that drought progression, the no drought, this is sort of the water balance. And you see as you go into the first summer of drought, tremendous withdrawals from storage, collapse of runoff. As you go into full drought, we have a shutdown of evaporation starting to occur as well, and runoff's gone to 0. So just an idea of what that summer drought looks like. Okay, so let's take some of these things we've learned playing with models in Bad Lake and other places and apply it to southern Manitoba to look at more modern tillage practices. And so I'm going to talk about zero-till with the tall stubble, the macropores, versus the old conventional tillage, which has occurred in that area. And Manitoba's never been a place that summer followed so much for moisture conservation as much as it was weed control and other cultural reasons in the past. Yet they still did summer fallow quite a bit. So South Tobacco Creek watershed, some of you may be familiar with it. It's in the Red River Valley Basin just north of North Dakota. So heavy glacial clay soils in here. There's an upland area and then a very, very flat. The Red River Valley is dead flat, it's bowling alley flat, and with this Manitoba upland up here. And I'm going to zoom into, there's a broader watershed which is going to look at South Tobacco Creek, a fairly small part of it. And so this one, the farmers have added extra instrumentation to make it possible to run a detailed hydrological model. They've also put in some detention ponds at the lower part of some of the streams to try to hold back water for water quality management purposes. The nutrient runoff from South Tobacco Creek has been implemented with some of the water quality problems in Manitoba, particularly heading down the Red River towards Lake Winnipeg. So the farmers are doing what they can, and it's well gauged. The river basins have a riparian forested zone around the edge, and then some of these detention ponds, as well as lots of fields through here and intensively cultivated zones. The tillage changes over time. The red is zero-till, and the green is just forest in here. There's been a slight increase since 2000 in that area, but a lot of variability year to year. So these zero-till areas range from 22 to 45% in there. And now they're becoming 8 to 10 years old, which is interesting for us because they should be developing a nice macropore structure, which should allow fairly unlimited infiltration conditions. And of course, zero tillage means lots of tall stubble as well. So the one thing we did, we wanted to test the model there. We ran this at the field scale over South Tobacco Creek, and there's a few snow surveys and depth surveys, and we're able to mimic those, match those pretty well. You can see that the cumulative snowfall is not anywhere near the accumulation of snow on the ground. That's the red line, the snow water equivalent, because of snow ablation and redistribution over the winter. When we look at simulated and observed outflow, we get fairly good results without calibrating the model at all. And this is encouraging. So we're running the model from measured physical parameters from the experience that we've had in Saskatchewan and various sites, and also from the careful measurements that are available in South Tobacco Creek. And this is an advantage of a physically based model because we don't have much in the way of parameter uncertainty in this case, and also we feel we can take the model into situations that haven't existed yet climatically and in terms of cultivation and still get reliable results from it. And when we look at that, we can say, well, all right, it's interesting at the small scales of Steppler, it's a 2 square kilometer watershed. We're actually getting some heavy rains up there in the escarpment and some substantial rainfall runoff. But as you go to larger scales at Highway 240 and then the 73 square kilometers at Miami it's now snowmelt runoff which is dominating. And since eventually we're going to want to put water quality into this model, we're very interested in those two pathways. So I'm not going to get into water quality here. And so now we can play around with it. So let's look at tall stubble versus short stubble impacts on snow accumulation. And the red line is tall stubble, and we get much greater accumulation where we allow tall stubble, at least in the high snowfall years. In the dry years, in the drought, not so much. It doesn't matter what you do in the drought, there's not much snow. So the snow management won't get you out of the drought, but it can influence the peak snowpacks in the wet years, is what we find in this environment. The impact on snowmelt runoff reflects that to some degree. All we've done here is increase the stubble height, and in the wet years we are getting much more runoff when we allow tall stubble in the basin, and in the dry years no real difference at all. Well, now let's add zero tillage. And we have to make some assumptions about it because it's still a little bit controversial. The gray line here is allowing unlimited infiltration in the spring. The black line is the current situation. And in between is an area of great uncertainty. It depends on the development of macropores, which depends how old the tillage, zero tillage practice has been going on. And it also depends a little bit whether there are hard pan layers which develop in there. And so that's the uncertainty range, but in general, one can reduce the flow by moving into a zero tillage situation here. And then finally, putting the small reservoirs, ineffective. They're too small, and we can easily discount those using the model as not being very helpful there. So we put it all together. We've increased the stubble height, which increases the runoff. We put in these reservoirs, which slightly reduce some of the peak flows. And we've allowed zero tillage, which may reduce the runoff. These are counteracting factors. We're calling them all BMPs, but they actually work against each other to some degree. And this is what we get at the end. The blue is the current condition with the BMPs applied if they're as fully effective as possible, which largely means that soils have full macropore development and higher infiltration rates. The red line is the runoff under the transitional situation. The green line is before the BMPs. So the initial response after the BMPs is actually an increase in runoff, which is not what they're hoping for, and then eventually some kind of a decrease, but whether we actually ever get there to that blue line is not certain. So a few comments to conclude. Just tried to show you a few examples of how soil moisture and water, soils and snow all interact in the Canadian prairies to produce some aspects of our hydrology. And the very important aspect is that spring runoff generation in the prairies is completely modulated by the fall soil moisture content and also any subsequent ice formation on top of those soils over the winter. That soil moisture then controls water availability for evapotranspiration, and the interaction of climate and soils then controls the development of hydrological drought. And it's the hydrology which shuts off first, largely because we have a more moderated impact of drought on the soil moisture conditions. You can take simulations of these things to assess what are called beneficial management practices. And I showed one example from South Tobacco Creek. And these can certainly, we can manage the impact of soil moisture on hydrology using BMPs, but there's a lot of uncertainty as to their effectiveness. And in fact, some evidence that some of them work against each other to some degree in that environment. So I think it's an area that requires much more careful study, but using both trials and simulations that allow us to get at the physics behind these things. And and in particular, I think it's not fair to assume that all soils are going to respond the same to zero tillage situations in terms of their changes to their infiltrability. And we really have a gap in terms of studies on the prairies as to how these things have changed. And the evidence coming back from a lot of farmers from the flooding in this last spring was that many reported a development of a hard pan layer below the rooting zone, which then developed a perch saturated layer during the flood, which may have increased runoff. At least that's what they're arguing. And so we need to investigate that next.